Hello, and welcome to this second lecture on our series on linear algebra. In this lecture, we're going to be talking about vector and matrix norms. Once again, this is presented by EDU Onyx. Now that we're kind of familiar with vectors and matrices, we've seen some of the notation, we can actually dive into some of the ways that they are used in machine learning. The first way that we are going to discuss is going to be norms. So the magnitude of a vector can be measured using a function called norm. And this magnitude comes up in machine learning, and it can be used a lot of different ways. Norms are used everywhere we need to describe the magnitude of a term, which is going to include when we define a loss function in terms of the magnitude of the distance between predicted and actual points. It could be used when we're defining a regularization term, which includes the magnitude of the weights to encourage small weights. There's many more applications. Norms are used in other areas of machine learning as well, other than just deep neural networks. For example, a support vector machine is going to use an L2 norm, which we'll talk about in a little bit, to calculate the distance between the discriminant and each individual support vector. All right, so that's a little bit about the why. Now, what exactly are the norms? Well, norms map vectors to non-negative values, so we're going to get positive results out. And also, the norm of a vector, intuitively, you can think about it as the norm of a vector x is going to measure the distance from the origin, 0, 0, to the point x. And this doesn't have to just be one-dimensional, two-dimensional. So, example, you don't necessarily have a two-dimensional point in a Cartesian system here. You could have the origin 0, 0, 0, and then the distance would be to the vector if it had three elements to that origin. That's just an intuitive way to think about it. It's going to be a distance or a magnitude from the origin to that particular vector. All right, so the first, we want a general formula, and that's going to be the LP norm. So this is a formal definition of the LP norm. When we have norms, they are often denoted, as you see on the left of this equation here, by the double bars. So this is the vector x. It's bolded, it's lowercase. That's how we know it's a vector. And we're taking the norm of it. And this, we're going to fill in different values of p. Here we're going to have 1, 2, all the way up to even infinity for p. And what we're just doing here is we're taking a summation over all the elements in the vector or the array and taking the absolute value, that's the single bars, over the x of I. So for each element, we take the absolute value, we raise it to a certain value p, we sum up all of those different results, and then we take it to the factor of 1 over p. So this is in general what we're going to be doing, but actually when we fill in different values of p here, we're going to get very different norms. So let's talk about the most common, and that is when p is equal to 2, we get the Euclidean norm, or what is more commonly known as simply the L2 norm. So this is going to be in general just the magnitude or distance in Euclidean space. When we have p equals 2, we sum up all over the square of all the elements and take the square root. So this is exactly the Euclidean distance that you might have seen in other applications. And this one actually comes up so often that it's typically referred to as simply the double bars x. You can drop the 2. If it's not specified, assume they mean 2, because this is above and by far the most common norm that you will see. So this is the Euclidean norm. Let's take a little look at an example here. If we fill in some of these numbers, for example, if we had the vector -1, 2, so a simple 2 points, we'd take the square of each of those and then take the square root and get out the square root of 5 as the magnitude of this particular vector. So really easy to do. And again, remember, we don't necessarily only have to have 2 elements here. For example, if we added a third, we would just have another term under this square root. And so that would be a vector of length 3. You could do this for a vector of length 500 and above and beyond. There is no limit to the length of the vector that you could use for a Euclidean norm such as this. All right, so that's just a simple example. L is equal to 2, however, Oh, intuitively, this is going to be the distance from -1, 2 to the origin. So like we mentioned before, Euclidean norm is going to give you a Euclidean distance from the vector to the origin. All right, so if we fill in some other values, we can have the L1 norm. And in cases where discriminating between small non-zero values and 0 is going to be important, the L1 norm comes in extremely useful. So the L2 norm that we just looked at, it's not going to increase significantly right around the origin because we are taking a square of each of those elements. In the L1 norm, we just get the summation of all of the individual elements. As a result, this is going to increase linearly right around the origin. And that linear increase is very useful because we can actually use it to discriminate between 0 and non-zero values around the origin, which in machine learning becomes very useful because weights that are equal to 0 and weights that are very small but not equal to 0 actually have a very significant difference. So the L1 norm is useful in machine learning because it allows us to tell whether or not we have 0 or slightly non-zero values around the origin. All right, so there we have L equals 1, or the P equals 1. We're not done. We can use the max norm, which is where we actually take P to infinity. So the L to the infinity norm is referred to as the max norm and is frequently used in machine learning. In this case, it's actually going to simplify to the absolute value of the largest element in the vector. And that we denote in this formula by simply the max of I, absolute value of that x of I, is going to be equal to our max norm. So you'll see this from time to time. And although P going to infinity seems complex, it actually simplifies down to simply the absolute value of the maximum element in that particular array. All right, we have the max norm, and we have the next one, which is the Frobenius norm. You might have wondered, well, we're talking so much about vectors, what happens when we have a matrix? And this is where the Frobenius norm comes in. And this is actually going to be analogous to the L2 norm of a vector. However, we are going to be doing it for a matrix array. So here you have the Frobenius norm denoted with the F, the double bars in the F. You also notice that this is indeed a matrix because we have a capital letter that is bolded. We talked about in the first lecture how you delineate a vector from a matrix. That's going to be the capital and the bold. And then we're simply taking the square root of the summation of all of the elements in that matrix squared. And so you see the square root here because this is analogous to the L over 2, and taking it to the factor of 1/2 again is just the square root. No need for the absolute value in here since we are indeed squaring all of the elements, which is going to return positive values, summing those all up, and then taking the square root. So the Frobenius norm is one that comes up in machine learning fairly frequently because it doesn't handle matrices. It actually comes up less frequently outside of machine learning because it's not often that you need to find the norm of a matrix. Typically in the math world or other applications of these norms, you're going to be dealing strictly with vectors. So the Frobenius norm, common in machine learning, slightly obscure in the rest of the world. All right, and that's going to bring us to the end. This is just a quick lecture on vector and matrix norms. In the next video, we're going to talk about how you can use these norms, the magnitude of these vectors, to actually normalize the matrix or the vector and actually produce what are called unit vectors. That's going to be one of the special matrices and vectors that we will talk about. We'll also talk about diagonal matrices. We'll talk about symmetric matrices, and finally orthogonal matrices as well. So stay tuned for that. Thank you very much.